Okay, this is Unit 6, Section 6.5, and we're going to continue looking now at polygons, and then we're also going to review SOHCAHTOA and our special right triangles for what we're going to do in Section 6.6 and 6.7. So our goal now is to classify polygons and review SOHCAHTOA, and so classifying polygons is similar to what we did classifying polynomials as well as triangles, is that these have a special name for them. So when we start out, we have the names for a polygon that has 3 sides. Okay, we name it by the sides that they have. So any object that has 3 sides is a triangle. 4 sides, no matter what it is a quadrilateral. Not all 4-sided objects are rectangles or squares, but those fall into this category. Then we have pentagons for 5-sided objects, hexagons for 6-sided objects, heptagon, I've also seen this as septagon, for our 7-sided object. 8 is our octagon. 9 is nonagon. 10 is decagon. And then anything else, 11, 12, 13, whatever it is, we just say it's an ingon. So if I had 11, it would be an 11gon. If I had 100, it would be a 100gon. We get kind of lazy at the end there. There are other names, but it's acceptable once you get beyond 10 to just use this notation for it. So one of the things that when I was in school that interested me was this idea of like September, October, November, December, and why they didn't match up to our 9th month, 10th month, 11th month, 12th month. And that's because we added July and August for Caesar. So Caesar really did kind of change our calendar by adding those in front, which then changed the Latin terms for those, where septa is 7. So originally September was our 7th month. Just a little tidbit there. And then our next vocab word, and what we'll be focusing on in this rest of this unit, is a regular polygon. So a regular polygon could be a regular quadrilateral, which would be the square, regular pentagon, regular hexagon. Any of these can be made a regular polygon if they meet the 2 criteria. And so our 2 criteria are all angles congruent. And so those are marked by our little arcs here, saying that this angle is the same as this angle all the way around. And, okay, it has to meet both of these criterias. All sides are congruent. So that's where we have our tick marks telling us this side is the same as this side all the way around. So this one, we would name this a regular, because all the angles and all the sides are the same. And there's 1, 2, 3, 4, 5, 6, 7, 8. We would name this a regular octagon. And so when we start looking at regular figures, they're going to have some special qualities that we can use to find their area, and then in turn be able to classify and understand them a little bit more. So practicing with that idea of what is regular and what is not, look at the following below and see if it's regular. So here we have a 1, 2, 3, 4, 5, 6, 7, 8-sided object. Is it a regular octagon though? On this one, it would be no, because it only has sides that are congruent, not angles. So while this is an octagon, it is not a regular octagon. Our stop sign is that regular octagon idea. On number 2, okay, we have a 4-sided object here, but is it a regular quadrilateral? Is that a square? And so this one also is no, because this one only has angles congruent. While this one does have 2 sets of matching sides, they're not all the same length. So this one is not sides. And our third one, we have a 1, 2, 3, 4, 5, 6 hexagon. And I have markings for all the sides and big arcs here they put for all the angles. So that I would say, yes, this is a regular hexagon. So regular has to have both those criteria. If we have one that has all the angles the same, but not sides, it's not regular. Same goes with our example that has all the sides the same, but not angles. The name for them is still octagon, quadrilateral, hexagon. We can add this if they meet the two criteria of congruent angles and congruent sides. One of the characteristics of a regular polygon is called the central angle. And this is the angle created by two radiuses or radii, I don't know, let's say radius, yeah, and the vertex at the center. All right, so the way that we find that is any central angle can be found by taking 360 divided by n. And n is number of sides. And so if I looked at our example, it says classify the polygon by the number of sides. So that's practicing our classifying up in the chart above. Sketch the regular figure. So what would it look like if it was regular? And then find the measure of the central angle. So if I have a three-sided object, I would classify this as a triangle. The regular figure would mean that all the sides and all the angles were the same, making that an equilateral triangle. If I drew in one central angle, here's the center, here's two radiuses going out to the vertices here, my central angle would be 360 divided by 3. And when I calculate that, this measurement would be 120 degrees from here to here. Okay, on number 2, we have a 6-sided object, which would classify it to be a hexagon. Okay, if I try to draw that, I'm going to draw out. And again, I know that my drawings aren't perfect, and I could use my cheating tool, but I know I want you to practice this as well. And so central angle, go up to the center, vertex to vertex, and find that measurement, 360 divided by the number of sides, which is 6. So the measure of this angle here at the center is 60 degrees. Number 7 is a heptagon, and I would accept septagon. And so now we need to add another side in there. So, okay, I need to be pointy, and then coming down, so 1, 2, 3, 4, oh, that's going to be 5. Let me try again here. Heptagon. It's harder to draw the odd ones, I think, because there's not a symmetry there. So 1, 2, 3, 4, 5, 6, 7. Ooh, that kind of bends. All right, I'm going to cheat. Do I have a cheater tool for it? 7. All right, I was getting close there. So my cheater tool, 1, 2, 3, 4, 5, 6, 7, I think I just wasn't going out enough there. All right, so central angle, if I go up to the middle and down vertex to vertex, I'm going to take 360, divide by 7, and I get a decimal. I'm going to round to the nearest tenth here. 4-sided object would be a quadrilateral, and our quadrilateral does have a special name when it is regular. We call that the square. Central angle, vertex to center, back down to vertex. 360 out of 4 is 90 degrees. And n equals 8. Classify this as an octagon. And again, I'm better at drawing the ones that are symmetric because I'm like, okay, they go out, they go down, they come back in. And see, there's my 8-sided object. Central angle, center, back down to vertex, 360 divided by 8. Should cut that in half, 45 degrees. And 6, now we have a pentagon. And okay, this one is going to go out, and I kind of drew that one when I was doing 7. So now I have 1, 2, 3, 4, 5 sides, central angle, up to the center, back down to a vertex. 360 divided by 5 is going to measure 72 degrees. All right, so we practice naming and classifying those and finding the central angle. Again, I'm not going to grade you on your drawings, so if you don't have the cheater tool here or you can't use that, it's okay as long as that object has 7 and we know we're drawing in that central angle correctly. The second part of today's lesson is reviewing using special right triangles or trig. So each one of these has a missing piece, and whether it's a special right triangle or trig, or what can always work is trig. So a special right triangle is meant to be fast if you know those patterns. So when we look at this, our two special right triangles, we have a 45, 45, 90 that follows the pattern of the legs are the same and you multiply by radical 2 to get the hypotenuse, or a 30, 60, 90, which says I have a short leg times radical 3, and short leg times 2 for the hypotenuse. If we know these and can apply them, it can be fast. Any other angle, we would use SOHCAHTOA. Okay, so this always works because it can be 30, 60, it can be 45, 45, any angle we can do SOHCAHTOA. This is meant to be faster if we know it. I'm going to use that as my T there. All right, so on number 1, we could do this 2 ways. If we saw the 60 degrees and knew that this was times radical 3, we could say that x has to be 5 radical 3. And that's where it's meant to be faster, if you know the pattern. If you want to do this consistently and just have the same thing every time, circle, label, and do the trig and say, okay, this is tangent of 60 equals opposite over adjacent, cross multiply, and we get x equals 5 times tangent of 60, and we'll get the same measurement. We get x equals 5 radical 3. Either one is a valid way to get that same answer, because in this unit, we're not going to stop here. We're going to continue to use this in our measurement for area. On number 2, 21 isn't special, so again, I have to do my labeling, adjacent and hypotenuse, and using trig, cosine of 21, to find that missing angle. Missing side length. So I have x equals 25 times cosine of 21. Again, I'm putting this in my calculator because I don't know what the cosine of 21 is. And I get 24.3 as that missing side length. And again, we're going to use this in our formulas for the next couple days. So that's why we're reviewing here. On number 3, when I circle this, I see 45, so I can use my special right triangle that says these are the same, which tells me x has to equal 4. But again, if you want a consistent way that does it every time, we have opposite and adjacent, and we can use tangent of 45 equals x over 4. Cross multiply, we get x equals 4 times tangent of 45. And on our calculator, that gets us 4. Same thing we got with our special rights. This is meant to be faster. This always works. So if we're quick at this, it really doesn't slow us down that much. On number 4, okay, I circle it and see, ooh, that's 60. So how do I go from long leg to short leg? I'm going to divide by radical 3. So using my special right triangles, I could get y is 20 over radical 3, so 20 radical 3 over 3, or use special right triangles, or use trig. We have opposite and adjacent, which is going to be tangent again. My tangent of 60 is 20 over y. So I cross multiply, I get 20 equals y tangent of 60, and divide by tangent of 60 to get y by itself. So in my calculator, I take 20 divided by tangent of 60, and it gets me that same value, 20 radical 3 over 3, which is approximately 11.5-ish for my y value. And again, special right triangles, one way to get it. Trig will work for any of these. On number 5, 39, as I circle it, nothing special about that, so I have to use my trig. Opposite and adjacent, and tangent will get me there. Tangent of 39 is 11 over x. Cross multiply, x times tangent of 39. Divide by tangent of 39 to get x by itself. And in my calculator, 11 divided by tangent of 39 is 13.6. So this length, which looks and appears to be longer, is longer in my answer as well. Number 6, I circle 60 and think, ooh, special right triangles. How do I go from short leg to hypotenuse? I multiply by 2. So if I go backwards, I would divide by 2, giving me 19. Here's special right triangles, or I can do adjacent and hypotenuse and do my trig as well. Using cosine for adjacent and hypotenuse, cosine of 60 equals adjacent over hypotenuse, and cross multiply. X equals 38 times cosine of 60, all by itself on x. So in my calculator, I'm going to put 38 times cosine of 60, and I get 19 as well. Again, special right triangles are meant to be fast, but I'm not grading you on your speed, I'm grading you on your accuracy. So if SOHCAHTOA is what you have down, that will work every time. If you feel comfortable going back from special rights to trig and seeing those patterns, you can use those as well. So on our last two, okay, we have 45 degrees, special right triangles, especially with this when I have the same. That's why it's faster. These should be the same, 13, and be done. If I want to apply trig, I'll get the same thing. Tangent of 45 equals x over 13, cross multiply. X equals 13 times tangent of 45. And in my calculator, I get x equals 13. Same thing. Special right triangles or trig. They'll be the same. And on our last one, 48, as soon as I circle, nothing special about that one. So I'll label, I have opposite and hypotenuse, which will lead me to use sine to find that missing side length. Sine of 48 is opposite over hypotenuse, and cross multiply. X equals 32 times sine of 48. And that's by itself, so I'll go into my calculator and type in 32 times sine of 48, and I get 23.8 as that measurement. I can't use special right triangles on everything. I can always use trig. So keep that in mind, and we're going to practice tonight reviewing our SOHCAHTOA and special right triangles, as well as classifying polygons and finding central angles are the main ideas for today. Let me know if you have any questions, and I hope you have a good day.